Welcome to this podcast on potential energy. So far we've discussed work and kinetic energy and how the two are related. You'll find that in some situations the work that you do does not show up as kinetic energy of an object or the change in kinetic energy of an object, and those are the situations that we want to consider today. Let's get started. On the screen you see an example of such a situation. I've provided for you two. One is the spring-loaded dart gun. Okay, so think of a dart that you load into the gun by pressing back against the spring. Okay, I want you to consider the work that you do versus the work that the spring does. Okay, so let's say your hand is coming from over here, right? So you're pushing it in. You're doing I will call that FU. Okay, you're doing positive work, right? Because the displacement's to the left and you're pushing to the left. During that time, the spring is doing negative work, right? It's pushing to the right while the displacement's to the left. Okay? Notice that at the end of this, the dart's not moving, right? So in the beginning of the situation, when you first loaded it in, it had no kinetic energy. And then at the end, even though you did positive work, it still had no kinetic energy, right? In other words, there are times when the work kinetic energy theorem is not sufficient, okay? But what we've done here is we've changed the configuration of the system, right? If you consider the system to be the dart and the spring. Okay, the similar thing happens when you lift a barbell, right? What happens there is you do some work, right? Again, you're pushing upward, okay? So arrow upward is to be FU, okay? Oops. F sub U. So you're doing positive work, right? During that same amount of time, or during that same period, right, the force of gravity, okay, is doing negative work, right? The net work during the time is zero, okay, in both situations. During the time that you're doing a certain amount of positive work, the spring's doing the same amount of negative work. During the time that you're doing positive work on the barbell, the force of gravity is doing negative work on the barbell. And so in each case, the net work is zero, and in each case, the change in kinetic energy is zero. But the configuration of the earth barbell system, right, or of the dart spring system has changed. And when that happens, okay, we say that there's a change in potential energy. So really, after here is the same old thing we've been after before, which is giving an account of energy. We want to become very able energy accountants, right? If work was done, you should be able to say, hey, this is what happened. Right, either the object's moving faster than it was before or slower than it was before. Or in this case, another situation, right, if the kinetic energy doesn't change, but the configuration of the system changes, then that work has gone to change the potential energy of the system. Right? So we have a relationship not only between work and kinetic energy, but work and potential energy. So let's quantify that now. I'm going to go to the next screen. Okay, we're going to take the definition of work, the formal integral definition of work. And we're going to say that we're going to define that work done as the change in potential energy, except we're going to put the negative sign there. We're going to say that the work done is the negative of the change in potential energy. Okay, and that goes back to, if I go back to the previous screen, right, it goes back to the force that was operating, right, during the time of this spring-loaded gun. This force here, the spring force, is doing negative work, right? During the time that we lifted the barbell, the force of gravity was doing negative work. So work done by the force and the potential energy are related to each other, but by the negative. Okay, we can write this a few different ways. I can expand this delta U as U final minus U initial, right, or U2 minus U1. And then we could write it this way very generally, right? If we're integrating from one position, right, S1 to S2, right? If we were in one dimension, we would just use X. Okay, remember S is the generic three-dimensional displacement. Okay, so I can write this a couple different ways. And then one more way here is, right, so that means if we don't integrate over one displacement to another, for example, infinitesimal displacement ds, right, we do an infinitesimal amount of change in potential energy du, and then we can rearrange this, okay, here to see that the force, okay, the force is related to the potential energy by the negative derivative, right? Or if you're talking one-dimensionally, we'll use this version more often. The force in, say, the x direction is the negative derivative of the potential energy function with respect to x. All right, like that. So you'll find that we actually use that particular version. We're going to come back to this nifty little equation later. We can apply this to a system in particular, like an example of a Hookean spring, right? A Hookean spring is simply a spring that obeys Hooke's law. So we have the force here, and what we can do is let's say we stretch this spring, right, from that configuration to, let's say we stretch it, right, like that, okay, so that this would be x1 and this would be x2. So what we can do is we can integrate, right, because it says that the potential energy, okay, the change of potential energy is the integral, okay, from one displacement to the other. Actually, it's the negative integral, right, of the force with respect to x, like that, okay. And when you do that, you'll see the negatives cancel. You'll see that you get this right here, 1/2 kx squared, which I think you'll recognize from last year, right? It was just given to you as a formula. Hey, the potential energy of a spring is 1/2 kx squared, right? Or alternately, this is a separate problem, but the potential energy, right, on Earth is mgh. Well, both of these expressions here, right, both of these expressions really come out of the general definition of the potential energy function. It just depends on which force you're talking about, right? In other words, each force has its own potential energy function that goes with it. Let's take a closer look at some other aspects of potential energy and the forces associated with them. Okay, it turns out that we can classify forces as conservative or non-conservative. So let me show you that right now. Take an example here of a skier on a hill. Okay, when the skier goes to the top of the hill, right, like that, the work that gravity does on the skier to get, as the skier goes to the top, okay, is negative mgh, right? So we can say the work done by gravity is negative mgh, right? And then when the skier goes down the hill, okay, the work done by gravity is positive mgh, right? So that the net work done for the skier to return back to where he or she started, the net work is going to be 0, okay? The net work is going to be 0. Now compare that to, here's a different scenario, the work of friction, okay? And that's what I have on the bottom here. The box is moving to the right, right? That means that friction is to the left, okay? So friction does negative work, right? Now come over here and let's say we go back to our start point, right? On the right, if the displacement is to the left, the friction force is now to the right, okay? And again, the friction force does negative work. So to get this box back to where it started, right, back to its start point right here, which is the origin, okay, when this box undergoes a round trip, the friction force does negative work going away from the origin, and then it does negative work again going toward the origin. It does negative work both ways. Notice how that's different from the gravity force in the skier scenario. Right, in the skier scenario, the gravity force did negative work when the skier went up and positive work when the skier went down. So that in the case down here, right, the total work, the net work would be less than 0. Right, the net work would be less than 0, whereas the net work for potential energy, gravity, is 0. We define a conservative force, right, as a force that behaves like gravity does. That when you go on a round trip, when you take an object on the round trip, the net work is 0, right? It's positive one way and negative the other, or vice versa. Okay, whereas a non-conservative force doesn't obey that, like friction. Friction is an example of a non-conservative force. A human's output, right, when you push on something, is an example of a non-conservative force, right? You push a box, and say you're pushing the box to the right. Okay, you do positive work, right, pushing the box to the right, and then you turn around and push the box to the left. You're doing positive work again. Right, so the total work that you do on the box is positive, not 0. So the work that you do is an example of a non-conservative force. The work of friction is an example of a non-conservative force, and whereas an example of a conservative force is the force of gravity or the force of the spring force, right, of Hooke's law. All right, one more thing about conservative forces. Conservative forces are path independent. Notice that if the skier goes on this hill here, okay, or on the hill that to the left, okay, either way, the work done by gravity is mgh. Okay, it's path independent. So another aspect of conservative forces is they're path independent. Okay, the last thing we want to look at today is something called types of equilibrium. So when you have a potential energy function, right, there are areas where the potential energy, where the force on the object will be zero. Okay, but what we want to look at is that equilibrium stable or not stable? So what we have here is a marble in three different configurations. Okay, one in a stable, one in a neutral, and one in an unstable. So what I want you to think about is if we take this object that's in equilibrium and we disturb it slightly, right? We give it a little displacement, and then we let go. What will be the tendency of that object once we let go? Will it tend back toward equilibrium? Will it do nothing? Or will it tend to move even further away from equilibrium? Okay, I think you can see the answer is pretty obviously here. Right? If we push this marble a little bit up the hill, right, so we give it a positive displacement, okay, when we let go, will it accelerate in a positive direction or will it tend back to zero? Well, it's going to roll back down the hill, right? It's going to tend back to zero. So when we have a positive displacement, we actually produce a negative force on the object, right? Okay. Now let's look at this neutral equilibrium situation, right? We push it to the right, we give it a positive displacement. Okay? And right, if we let go, nothing's going to happen, right? It might, it'll probably continue rolling, but it won't accelerate that way. In other words, the potential energy function is not tending toward or away from the equilibrium point. And then finally here we put this marble at the top, right? If you give it a positive displacement, okay, the force is also going to be positive, right? It's just going to tend further and further away. So these are the definitions of equilibrium, stable, neutral, and unstable. Now you can perform a quick math test to determine whether the equilibrium is stable, neutral, or unstable. And it has to do simply with the concavity test, okay, applied to physics. So if you're familiar with the concavity test in calculus, we're going to use a very similar thing here in physics. So let me show that to you on the next page. All right, so it has to do with, like I said, we would come back to this here, right? So we're going to use that. And basically, we're going to take the derivative of that function, and the only difference between math class and this class is we're going to take the negative derivative of the function. So in other words, you're going to have a stable equilibrium if the negative derivative of the potential energy function, okay, or we're taking the derivative of the force here, right? If that's greater than 0, then you have stability, right? If it equals 0, then you have a neutral equilibrium, and if it's less than 0, then you have unstable equilibrium. So we're basically applying, right, this is the second derivative, right? So we're taking the second derivative of the potential energy function, but notice that we're taking the negative derivative to get the force, and then we're taking the negative derivative again to get this concavity test. So that's the only difference is, again, you're taking, just like math class, you're taking the second derivative, but you're just taking the negative second derivative. If it's greater than 0, then you have a stable equilibrium, or 0, or less than 0 will give you an unstable equilibrium. There you have it, potential energy.